Good morning, students. Here another lecture of antenna design. This class will cover two types of antenna, that is Yagi-Uda antenna and rhombus antenna. As you can see in the outline, rhombic antenna construction special features, in Yagi-Uda antenna construction special features. Before going to kinds of antenna, we should know what an antenna is. Antenna is a device that converts RF electric energy into EM wave. RF means radio frequency. An AC signal can have many frequencies, but if an antenna desires a signal to be converted to EM wave, then our signal must be of radio frequency range. Then only it can be converted into EM wave. So the basic two antennas today we are going to discuss is about Yagi-Uda antenna and rhombic antenna. Yagi-Uda antenna looks like this. As you can see, there are three basic elements in Yagi-Uda antenna. One is directors. The distance between those two elements, those kinds of elements are fixed. These are the formulas by which we can have an idea that how the elements in the Yagi-Uda antenna should be spaced. Like the reflector length should be 0.058 lambda to 0.5 lambda, means the length of the reflector. And the driven element or the feeder, the second one, that should have a length 0.55 lambda to 0.58 lambda. Lambda is nothing but the wavelength. Wavelength means at what frequency the antenna is going to operate. Accordingly, the frequency is equal to C by lambda. We have a lambda value for the operating frequency. So that lambda value is related with the reflector feeder element length. Directors length are many because as you can see there are many directors one by one. So the size of the directors vary like 0.45 lambda, 0.40 lambda or 0.35 lambda, like that. Next slide we will see how the number of directors actually help in getting a good directivity. Before that we should know another interesting terminology, parasitic element. As you can see I have given question mark to the parasitic element. Why? Because in the before slide you have seen, if I will refer to this picture, the feeder element is connected with the source, means this is the only element that is going to convert that energy, means RF electric to EM. Other elements, reflector and directors, are actually not connected to source but help in giving the directivity. That is why that is called parasitic elements. Parasitic elements means not connected to source but help in doing the job. As they are not connected to source, they are parasite because they depend on feeder element for the energy of conversion. So you can see the radiation pattern of the Yagi-Uda antenna will look like this, like a flower petal. This is the main lobe, and in this direction the antenna. And these are the side lobes, and this is back lobe. Though we don't intend to have those side lobes and back lobe, but generally this happens. So to avoid those side lobes and the back lobe, only the reflector is used. That picture that I have shown in the earlier slide, you see in the earlier slide it is reflector length is bit bigger. The bigger size of reflector just only helps to reduce the side and back lobes, because our target is to get only the forward direction lobe or directivity. The more number of directors we have in the antenna gives more better directivity, because directors are having the leading property, means current leading property, and reflector is a lagging property. So that is why the reflector obstructs the lobe to go to backside and the director helps to move the signal in a forward direction. That is why leading and lagging helps the Yagi-Uda antenna to get a better directivity. Of course, when we are going to design an antenna, we should know what are the good points and what are the bad points of any antenna. Because whenever we are designing the antenna for any application, whether that is suitable for that application or not, economically good or not, size wise good or not, frequency wise good or not, everything we should take into account before applying it to any specific application. So for that I have listed down some of the good and bad points of Yagi-Uda antenna. The good points are many as compared to bad points, but we should know all the points. Good points means highly directive, because as we know, the more number of directors will keep after the feeder element, it will give good directivity. So good directivity, very high gain, and lightweight because the total Yagi-Uda antenna is made up of aluminum metal. Aluminum is very light in weight. That is why the total antenna structure becomes very lighter in weight. And wide bandwidth. The frequency band operation is very good so that we can use at a remote application also it can be used. So wide bandwidth. Less good points mean bad points, though in a assertive way I don't want to tell any disadvantage about Yagi-Uda antenna because this is such a successful antenna. The bad points or disadvantages are very less, so that's why I have given the terminology less good points. Low front to back ratio, prone to noise, and big in size for required gain. This is a very valid point. You must have seen when you were in the childhood, your grandparents were using such kind of antenna in the terrace, and the size of antenna was very high, very large, and to get good directivity or to catch the remote signal, the antenna size intend to be much bigger. So according to frequency operation, the more number of directors will give good result, and ultimately the antenna size becomes big. That is why it is a less good point about an antenna before as compared to other good points. Um, if we will see the types of Yagi-Uda antenna, Yagi-Uda antenna main elements are three. One is reflector, another is your feeder element or the driven element, and many number of directors. But as I said, the more number of directors will help in getting good directivity. In that context, the total Yagi-Uda antenna has been divided into many categories. Means it is a three element Yagi-Uda antenna. As you can see, only reflector is constant, one in number, dipole is constant, another one in number, but director is here one. But in 5 element you can see there are 3 directors. Means what? Director number got changed. 1, 2, 3. In 7 element it is 1, 2, 3, 4, 5. And in 9 element it is 1, 2, 3, 4, 5, 6, 7. So only directors are changing in number. Reflector and feeder element are constant. They need to be 1 in number. The more number of directors, the better activity it has. So after completing about the Yagi-Uda antenna, that concept of Yagi-Uda antenna arranging the directors in twisted into a rhombic manner. If we will use 4-wire antenna in a rhombus shape, then it will give a structure like this, and it is called a rhombic antenna. But we have to terminate the rhombic antenna with a resistor RL, and we have to feed the antenna like this. Feed line is this. So what is the best feature? Because here individual antenna, individual wire is an antenna. This is 1, 2, 3 and 4. 4 wires can act as an antenna. They will have a radiation pattern in their own way as it is shown, but the ultimate radiation pattern is in the diagonal of the rhombus. Because it is a rhombus, it has a diagonal like this, and the load where the feeder is there, when the load is terminated, in that direction only the resultant directivity will be. So the resultant activity is same as Yagi-Uda antenna as we have seen in the last slides. Same Yagi-Uda antenna will have the rhombic antenna structure of directivity, but very good good point. Many number of good points are there. That is, it consists of greater directivity. Bandwidth is very high as compared to last Yagi-Uda antenna, and it is very useful for point-to-point communication. That was not there in the earlier antenna design. Here also we will discuss a few good points and bad points, because as I told in the earlier slide, never an antenna design is successful if we are going to discuss about the good points and the bad points. In the directivity context, in the size context, in the economic aspect context, in the application area context, in the wavelength requirement context, these are the contexts where we should discuss the advantages and disadvantages of any kind of antenna. Here also, the rhombic antenna has few good points. Input impedance and radiation pattern are relatively constant. This is a very good strong point in any antenna, because whenever we are designing an antenna has a feeding line. So if the impedance and the load is not properly matched, then the signal will be reflected. That means what? If I am striking a ball to you and you are not catching the ball, then what will happen? It will strike your head and rebound back to me, and it hit my nose. Then my nose is bleeding. So as a source, I am unsuccessful. That is why if the source and the load are properly not matched, impedance is not matched, then the antenna design whole concept is a failure. So here in rhombic antenna, this is a great advantage that automatically due to the structure of rhombus, the input impedance and the load impedance are perfectly matched. That gives a better directivity and it is constant. It doesn't vary with the variation of frequency. In multiple, yes. Another very good point is if with one single antenna the impedance is bit deviating or we are not getting the proper directivity, then it may so happen that we can connect more number of input, rhombic antennas in cascade. That is called cascading the rhombic antennas. Means one antenna is not successful, we can connect 1, 2, 3, 4 like that to get our desired directivity. Simple and effective transmission. Signal transmission is not at all difficult because we can polarize the rhombic antenna either in horizontal manner or in vertical manner. If it is horizontally polarized, then radiation pattern is in horizontal axis. But if it is vertically polarized, it will have a directivity at an angle, and that angle depends upon the height of the poles on which we are keeping the rhombic antenna. So that is why our effective and simple transmission is possible in rhombic antenna. But as well as it has some disadvantages, though I have used the points word less good points, means it actually these are disadvantages, but this is less good points. Requirement of large space. Why? Because four corners we require four poles and we have to polarize it horizontally or vertically. It requires a large area to be connected, and I told we can have a cascade connection also. If with one antenna our problem is not solved, we have to use 3 to 4 antennas. Then in that scene we have to have a large space. That is a first drawback. And reduced transmission efficiency due to this more number of cascade antennas will be there, feeding will be single, that then transmission become slower. That happens. Maximum radiated power along main axis. In the horizontal axis maximum power is there. If we want broadside radiation, it is not possible because as I told, rhombus has a diagonal and in that diagonal direction only the signal gets propagated. That is why the maximum radiation occurs in the horizontal axis. So this is a weak point also. Wastage of power in terminating resistance. As we see, you can see the diagram. Here I told there has to be a terminating resistance because if there would be no resistance, then signal which is going from the feeder to the space, it has to be absorbed by the terminating resistance. But due to that course also, maximum power is absorbed. Means if it is sending 0.25 milliwatt, then from 0.25 milliwatt maximum power is absorbed in the load, rest is being radiated. So we have to have much transmitting power to have better radiation because the signal is lost in terminating resistance. So these are the good points and bad points or less good points in rhombic antenna. So students, we discussed about two basic antennas of our literature or in a third year WPVC paper. We have many kinds of antenna, but the basic two antennas are this, who has greater bandwidth and better compared to other antennas. So I hope you will try to relate the construction and the good points, the bad points of Yagi-Uda antenna and the rhombic antenna. Thank you very much.